Hey, welcome back to TSS Garage. I'm Zach Chrisman. Today we're going to take a look at the Hofmann 7100 through 7800 series of weight class balancers. Today we're going to focus on the 72, 4, and 600 series, and let's take a look and see what they have to offer. Before we get going with talking about the machine, how it works, the user interface, I really want to dive into proper tooling selection and why it's important. I'm going to use this lighter passenger car wheel as an example. Generally speaking, we want to take a wheel assembly and we want to cone or collet it from the rear. It's not usually recommended to grab a machine interface from the front simply because that's not how it goes on the vehicle. If you can see inside of here, there's actually a machined lip that accepts the hubcap, and that's not the machine center line of the wheel. And that's one of the reasons we want to look out for that. The second, we want to deal with something that's low taper. Low taper allows us to ramp up to center much more quickly than something that's got a high taper to it, such as a standard cone. Standard cones can often lead to a slow ramp up speed, which allows two converging angles to get pinched off, if you will, before when too much torque's applied to the wheel before the wheel has hit the backrest or found center. This can often lead to a user chasing weight or wildly inaccurate centering of the wheel assembly and lead to someone questioning their results. So just make sure that we're using good practices here and using collets when necessary, possibly a pin plate instead of a pressure cup, and trying to apply those principles as often as we can. Moving from the 7200S to the 7400L, there's a couple of obvious things. One is we get an upgraded weight tray, a little bit larger, a little easier to store some goodies and keep clean on the side. Integrated weight plier holder, keep my scraper and often my tape weights over there on the right hand side. We're gonna go ahead and tool this SUV wheel up just like we would on the lighter guy using a collet rather than a standard cone. So I'm gonna grab the collet that's recommended for this wheel. I'm gonna tool this wheel up exactly like I did the previous wheel. You can look that data up in the Easy Collets app. It's a free resource available on iOS and Android devices. It's got a nice drop-down diagram. You select what make, model, year, and vehicle you're working on. It'll tell you use collet 4B in this case, for example. It'll tell you the hub bore diameter. It'll even tell you what the 6 on 135, 5 on 4.5, whatever the lug stud pattern you're working with. So it helps to shorten the hunting curve there. I'll check my fitment. There's two sides on every collet, right? So you don't want to use a side that puts you too close on the outside edge or too far in on the inside edge. You really want to step down or step up. Really want to try to get right in the middle there. Sometimes if you're too far in, like we were on that previous wheel, we might have protruded too far and come into contact with that machined hubcap interface. That's something you want to keep an eye out. That will lead to some mounting discrepancies. So we're gonna go ahead and put this wheel on. This time we're gonna use one of our speed plates. Highly recommend. Show these here briefly in a moment. Allows me to very quickly find the lug stud bore, and then I'm going to take my wing nut with the bearing on there, not the pressure cup, and I can go ahead using the holder. I can hold the shaft, give her a couple spins, tighten her up. We're on there. This is the most accurate you can get. We're emulating how this wheel assembly goes on the vehicle by applying pressure at the lug stud bores even and accurately, as well as a low taper collet in lieu of a cone, is allowing us to not only find center quickly, but it's also applying pressure at the correct points on the wheel assembly. If we balance a wheel assembly with a cone and we're slightly off of center and we balance it on the balancer, it doesn't mean the assembly is not balanced. It means it's balanced on that rotational axis point that's true zero when it was on the balancer versus what it might be on the vehicle. That's why it's so important to use good tooling. Continuing on with the machine, again, you got the larger weight tray. The buttons have been integrated more to the top. You still have a raised video display. Everything else, for the most part, user interface wise, is still the same. Escape will always get us back to the home screen. We're gonna take our SAPE arm, and in this case, we're gonna touch the inside plane, go to the sticky plane, we're good to close our hood at this point. We don't want to touch anything here dimensionally and say, hey, this is a 18-inch wheel, not a 17.5. The reason for that is the machine's actually taking into the generalizing the dimensions. It's rounding to the nearest 1/4 inch based on where I'm telling it I want the counterweight to go. The dimensions of physically what's on here really doesn't matter. It doesn't matter if it's a 24 or a 16-inch wheel. What matters is where I told it I want the counterweight to go. Second thing to note, you'll notice the machine's designation 7400L. L stands for laser, and the 7200 was a 7200S. 7200S, S stands for standard. L now will give us a laser pointer to place the weight. So when I close this hood to perform the initial spin, we're gonna get our initial spin cycle, very quick, 6 seconds. Boom, there's our data. Again, stop on top, it stopped really close. We're gonna push it forward, 3/4 of an ounce. We can grab our 3/4 ounce weight, nail it on, and then bring this down until it highlights. Once it highlights, we're gonna see the laser pointer telling it exactly where to place my weight. Again, we're in a situation where we have a 6-spoke wheel. We may or may not like the placement that the machine has selected for weight. We may see that. So what I can do is I can go up here and I can tell it by hitting F1 until I get to 6 spokes, put a spoke exactly at 12 o'clock, hit F5, go to split weight mode. Now, when this thing goes into putting a weight, we're exactly behind the spoke, out of the way, looks great. The machine's done the math, recalculated what the weight parameters need to change because we're changing distances, so it takes all that into account. Other options still include the ability to change your ALU mode during your spin. This is really to be kind of generalized. And if I was doing a spare tire, a trailer tire, a steel wheel with nail-on weights, it's okay to do that here. But if you're ever gonna change anything where we told the machine where the exact counterweight needs to go, I would go back and start over and acquire new data points. Because when you hit F2 and change the weight, the machine has to approximate the new location of counterweight placement, so it's not as precise. Let's say, for example, we've done a sticky weight application here where we've just touched both planes. It sees that. I'm gonna go ahead and do my initial spin. Let's say at this point I wanted to say, oh, you know, I just wanna go ahead and move to a static balance or something like that. Just simply hit F4. Now, when I select this, you'll notice that the laser, it's not gonna scroll to anything. It's up to the user to place that weight at an appropriate location along that parallel. And in this case, I would recommend in a sticky weight application, center mass of the wheel as possible. That way you're not adding a bunch of weight and inducing dynamic instability at the same time. Outside of that, I would highly recommend that individuals be taking advantage of F3, which is the fine resolution. What that's going to do, it's going to take care of any residual round off that may be found in the wheel and tire assembly. A lot of times we may or may not encounter a vibration situation, depending on the tire's diameter, the mass of the wheel and tire assembly, and the type of vehicle it's on. If this tire came off of a Honda Accord and it was 4.5, 26 inches in overall outside diameter, that frequency range is going to be somewhere in the higher echelon there, 15, 16, 17, maybe plus hertz. And so that's going to be those scenarios where you have someone come back and say, hey, when I get to 78 miles an hour, I feel it in my floorboard. I can see the headrest jiggling, my cup of water's twitching in the cup holder, those types of things. On larger wheel assemblies, you're going to see that frequency come way down, 3, 4, 5, 6, 7 hertz. And that just has to do with their overall speed. The reason I bring that up is because when you have a wheel and tire assembly that is a little bit smaller in diameter, if we're utilizing F3 after we've balanced, let's say we did a 1/4 ounce and a 1/2 ounce, and we put those on there, and we still don't have that OK showing up in the middle of our tire, which I'll demonstrate here shortly, it's telling us that there's still some residual static imbalance in that assembly. So if I hit F3, it's going to allow me to go in and look at what exactly is left on the table to get all of the instability out in that assembly. I can hit F4 and toggle between dynamic and static modes. But once I'm in static mode, after I've done my dynamic balance, I can hit F3 again and know that I need 2.95 ounces, for example. Well, in the case that I've put on an ounce, and maybe I have a quarter left over here, let's go ahead and put that quarter on. That's gonna trim the fat, if you will, and really limit those smaller wheel and tire assemblies from encountering some type of a resonant frequency issue at higher speeds. Really help to tone down those comebacks. Just a little more of a deep dive into some of the intricacies of putting out good balance material, even though we can do that with any level of balancer that we're using. That sums it up for today. Thanks for hanging. We'll catch you guys on the next one.